Hello students, welcome back. We went through some algebraic structures in previous videos. First, we went through groups. These three properties. And then an additional property here will form a abelian group. And then ring theory. We have to have an abelian group under the addition. And as for the multiplication, well, we are just starting, so we assume only the associativity. And then distributivity is there to connect these two operations together. Now, we only have associativity, so adding more conditions, we're going to get stronger rings, more specific rings. Adding in commutative rings, adding in the commutativity of addition, we get commutative rings. And adding in the multiplicative identity, you're going to get the ring with unity. And then if you add in the multiplicative inverse as well, then you're going to get a field. But before that, as an intermediate step, you can add zero divisor property, and that'll turn out to be something called integral domain or factorial ring. And then finally, if you include the full-blown multiplicative inverse as well, then you get a field. So we have a abelian group in both ways, additive and multiplicative. So here's a summary. Field belong down here. And then we went through some examples too. The next algebraic structure that we are going to go through is vector space. And this is something we are going to cover in linear algebra. By the way, groups and rings, those will be covered mostly in abstract algebra 1. Field theory and some advanced ring theory will be covered in abstract algebra 2. Vector space here, and this is going to be the topic for linear algebra. So neither abstract algebra 1 nor abstract algebra 2 deal with this vector space. This is for linear algebra. And we have to have vector addition and scalar multiplication. Vector addition is internal binary operation. Scalar multiplication is external. We have to consider additional set, and that has to be a field. So scalar is coming from a certain field. In linear algebra class, we usually deal with the scalars from the set of real numbers, but we can consider complex scalars too. We have these conditions, and these four properties do not go anywhere. We have to have abelian group under the addition, and as for the scalar multiplication, we have some distributivity, some associativity, these kind of things. And then finally we have unity, the multiplicative identity. If you multiply by 1, you don't change anything. Examples include Rn, the usual n-dimensional vector space that we deal with in linear algebra class, and to a certain degree in multivariable calculus as well, even though over there we did only up to R3 at best. But then again, there are other examples, matrices, and then the space of continuous real functions, and then C1, C2, C3, and so on, differentiable and continuous derivatives, twice differentiable and continuous up to second derivatives, and so on and so forth, all the way up to C infinity, which means infinitely differentiable. And these kind of examples form a vector space. So the linear algebra and all those theory about vector spaces can be applied to differential equations and analysis as well. Those are vector spaces. Next topic, modules, and I don't know whether we'll be able to cover this in abstract algebra 2, but we'll try. If we do open abstract algebra 2, by the way, in any case, if you do, then I'll try. It's very, very similar to vector spaces. After all, we have vector addition and scalar multiplication and all. Let's change color into black. But the scalar is coming from a ring, not from a field. As for the conditions, pretty much the same. We have an abelian group with respect to addition and distributivity, everything pretty much the same. And if the ring has unity, then 1 times a vector is itself. We get all those. So basically the same as vector space, except that the scalar is coming from a ring. So basically, if you multiply by 2 to stretch a vector and double the size, that's okay. But if you shrink it by multiplying 1/3, you can't do that because this is coming from a ring. Examples include Zn, you see, you can do multiplication but no division in general, or matrices with integer entries, or matrices with polynomial entries with real coefficients. This one here, this one is going to be important in abstract algebra too, if we actually get there. Anyway, this one is important particularly. Okay, that's modules. And then the next topic is algebra. And this algebra is not the same as this algebra there. This is not a field of study, it's just an algebraic structure. And who named it this way, I have no idea. And whoever did probably is regretting it by now. An algebra is a vector space with a new operation, a vector operation. So a vector space has 2 operations, vector addition and scalar multiplication. Algebra has 3, vector addition, scalar multiplication, and vector multiplication. Can you think of a vector multiplication you went through in calculus? In multivariate calculus, you did cross product, don't you remember? Cross product. That's an example of vector multiplication. Another example of vector multiplication is matrix multiplication. And they are very, very different vector multiplications, by the way. I'll show you in a moment. Let's see. They will have to satisfy all the properties of vector space, of course, but these 3 additional properties associated to vector multiplication. You see, VS1 through VS8, they're all about addition and scalar multiplication. And all those must be satisfied, yes, because after all, any algebra is a vector space. But then again, we need these 3 additional conditions. Distributivity of vector multiplication to the right and to the left, and then the associativity of scalar multiplication. So, I don't know whether this is associativity or commutativity, I don't know, but anyway, I can multiply scalars first and then vectors later. Please note that we have only these. We do not have any standalone properties regarding the vector multiplication, not even associativity. So, if this vector multiplication is associative, then we say this algebra is an associative algebra. But in general, algebra need not be associative. An algebra is called commutative if the vector multiplication is commutative. In general, they do not have to be commutative. Let's see, I think you know some examples of multiplications that are not commutative. What is it? Composition, that's one example. Matrix multiplication, that's another. Yes, matrix multiplication will give you an associative but not commutative algebra. Now, can you think of an example that is non-associative multiplication? Here's some examples. R3 with addition, scalar multiplication, and also the cross product. Okay, addition, scalar multiplication, cross product. That's going to form an algebra, and this is going to be a non-associative algebra because cross product is not associative. It's not commutative either, as a matter of fact, but it's actually let's see, anti-commutative. So you can get to somewhere because if you just remove negative, then they are similar. So in terms of size, they're the same and things like that. Let's go back to where it was. But as far as associativity is concerned, no way. So that's an example of a non-associative algebra. There are more. The space of continuous real functions or differentiable or infinitely differentiable real functions and so on. They're all algebras. And these are commutative and associative algebras because the multiplication is, after all, coming directly from real number arithmetic by multiplying the function values. And because of that, the algebra this algebraic structure algebra is very, very useful in analysis. So it's kind of like this. Algebra is more important in analysis than in algebra. Does it make sense? Algebra is not that important in algebra. Algebra is more important in analysis than in algebra. Does it make sense? Whoever named this algebraic structure as, quote, algebra, unquote, created all this mess. If somebody named it a little bit differently, it's a little bit stronger vector space with multiplication and whatever it was named, then there wouldn't have been this kind of confusion. But sorry, it's too late to change that. All right, so much for section 2. And we included some preview or overview in Abstract Algebra 2 as well. And that part, of course, is optional.